Hello and welcome. Today we're going to be talking about an example of a complex eigenvalue problem. Okay, so you probably know, of course, now that we have problems like A times V is equal to lambda V. And typically in the first examples, we usually see lambda being a real number of some type. Okay. But we know that the lambda values come from a characteristic polynomial, which is the determinant of a minus lambda I. Of course, if we have an n by n matrix, we know that this is going to be a nth order polynomial. I should say that we usually see just examples where lambda is real in our first examples of this when we're showing students this. But in general, what we get is an nth order polynomial. So it's going to be something an to the nth power plus an minus 1 to the n minus 1th power, all the way down to a1 lambda plus a0 is equal to 0. We know the fundamental theorem of algebra, FTA, says that basically there are always n roots to an nth polynomial. Okay? And the key thing here is that some roots, lambda, could be complex, a plus I, B, like that. And if you get a root like this, you also get a conjugate root. So you'll get lambda is equal to a minus I, B as well. What we're saying here, of course, is basically complex roots. First, they can happen. They can happen. First and foremost, they can happen. And when they do, they come in pairs. Okay? All right. So, and again, they are, if we just have a general polynomial here, which if you can dream up a characteristic polynomial, you could probably find a matrix that could create that characteristic polynomial. Certainly these are possibilities. So the question that we have is, what are we going to do about them, and how do we solve for the eigenvectors, and what do they mean? Well, the what do we mean question I'll save for later, but for now we're just going to do an example to show how it works. Okay. All right. So it turns out the final thing I want to say about this is that the v vector will also be complex, and it will have both a real vector and then also an imaginary to go with it. Okay. All right, so let's go to a new page here and do an example. And we're just going to go do a simple 2x2 example. 1, 1, 2, and then negative 2 down there. Okay? So this will be a simple example. We'll show how this works. It won't take too long. Okay. All right, so we know that the characteristic equation for A will be A minus lambda I. We're going to take the determinant of that, and that gets us a 1 minus lambda on the diagonal there, and a 2 and a negative 2. We get a 1 minus lambda, quantity squared, plus 4 is equal to 0. Right, so this polynomial here, we haven't quite foiled it out all the way, but we actually don't need to. What we actually have here is a lambda minus 1. We can always flip the sign inside of that square there. And we can move the 4 over to that side. And now what we're going to do is, of course, we're going to square root both sides. But, of course, when we do so, we have to admit that we could have a plus or minus value come out of it. And then we have a lambda minus 1 is equal to plus or minus root negative 1 times 4. And that gets us a negative 1 root in there times 2. And, of course, that's going to be a plus or minus 2i. Altogether, what we have here is lambda is equal to 1 plus or minus 2i. I always said that they come in pairs. Okay, so that is certainly true. They come in pairs. All right, the next thing we're going to do now is, so these pairs, then I have to actually label that as lambda 1 and a lambda 2 there. So here's the other key fact I'd like to, and you could probably anticipate this, but I'll just say it ahead of time. The eigenvectors also are complex conjugates of each other. So V1 will be A plus IB. Then it also implies then that V2 will be the same A vector plus, or sorry, we got to undo that, minus IB. Okay, right. So it boils down to then we got to figure out what this A vector is, which I'll call alpha and beta. Okay. And then we also have to figure out, so we don't know what that is yet. We also have to figure out what the B vector is, which we'll call gamma and delta for lack of other letters. These will work just fine for us. Okay. All right, so we don't know what those are yet. But we're going to solve it just like we normally would. We're just going to find, all we have to do is solve for one of the eigenvalues, and we're getting to get the other eigenvector for free because all we have to do is conjugate the first eigenvector. Okay. So our question was, our matrix was 1, 1 on the diagonal, and then negative 2 there and 2 there, right? And now we're going to subtract the matrix, which is lambda I, so it's going to be 1 plus 2i, 1 plus 2i, and then 0 there. And then we're going to now multiply by v1, okay? All right, so we should be able to solve this, and that's going to be equal to 0, 0 there. Okay. All right, so remember, complex arithmetic is a little bit more complicated, but you just have to be careful and keep track of it all. Let's see if we can simplify this matrix a bit. We're going to get here minus 2i, 2, minus 2, and then we're going to get a minus 2i here. And that's going to be equal to v1, which we said was equal to a plus ib. Okay, and we don't know what that is yet. I think we can figure out how to solve this. Okay. Another way to write this is to actually write v1 is just equal to, again, for running out of letters here, we'll use c and d there. And then we're going to allow basically c and d to be complex values. All right. So maybe that will be a little simpler for us to figure out. Again, there's many ways to go about this, how you want to approach it with what notation. So the question then here is, we want to find a c and a d that make this linear system 0. It seems, though, if I look at that, it seems pretty clear that if c is equal to 1, that would imply that d has to equal just I, right? So my v1 I can write as the following. It's going to be 1i, like that. I can, of course, rewrite this as a real vector plus I. So there's my A and there's my B. Okay. Now let's give this a go. So I found all the things I need. So lambda 1 is going to be 1 plus 2i, and it's associated with the eigenvector v1 is equal to 1, 0 plus I times 0, 1. Okay, and again, we get lambda 2, which is equal to 1 minus 2i. V2 will then be the complex conjugate of what we just found. So we have no other work to do. We're done. So we're going to have 1, 0, and then we're going to have a minus I, 0, 1, because that's the conjugate of what we had from before. Okay, it might be worth our time to just actually see about, it'd be good for us to actually work out that this is in fact an eigen vector for the problem. So let's actually just go ahead and check what's going on here. So let's give that a good check. We have 1, 1, 2, negative 2. And now we're going to multiply by the vector. And I'm going to use this form because it's a little simpler for my v1. And that's just 1i. Of course, I multiply that in. That is my v1. That's my a. And now I'm going to get from it 1 plus 2i. And then we're going to get a negative 2 plus I. What we can see from this, though, is what if I actually, I see right away that we have here, that is exactly lambda 1 right there. But the question is, how do I extract out from there what this is? Well, what I note, though, is remember that I times I is equal to negative 1, right? So what I'm going to do is actually factor out I from this. So if I take an I outside, then I'm going to have a 2I there plus 1 right there. The other way I can write this is actually, of course, 1 plus 2I. And we can see, of course, that is my lambda 1. So putting that all together, I'm going to get a 1 plus 2i. I can factor out of both of those top and bottom entries, and I'll have a 1i right there. All right, so that does actually verify that that is an eigenvector for the problem. The meaning of this, we won't get into in this problem. I just wanted to go through how you do the complex arithmetic and how you solve for these problems. And you can see now that it works very much like everything you're familiar with real numbers. It just, you have to keep track of the real and imaginary parts of everything as you're going through the problem. So I hope that was illuminating, and we'll do more examples where we can show the meaning of these complex eigenvalues, what their actions are, how you can interpret that in another video.